All right, now that we have talked about what we know about charges, we've seen how to move charges around, we are ready to talk about how to characterize the force between charges. Usually in this class I will refer to this as the Coulomb force, but occasionally I will call it the electrical force. These are the same forces. The Coulomb, after Charles Coulomb, or the electrical force. We know that it arises between two charges, and I'm going to write down the form of this, usually subscripted with a C, but like I said, occasionally subscripted with a capital E. The Coulomb force is equal to this, K, which we'll talk about, times Q1, Q2, over R1, 2 squared. And to make this a vector, because it's a force, it's got to be a vector. Let me add the vector symbol here. And now we'll add this R hat here. Now, for some of you, you might have not seen this sort of vector notation before. I have a separate video over unit vectors and how to read those that I will post that you should watch. We'll go over it briefly here in just a second, but this is a vector symbol, or this is a vector with a magnitude of 1. Its sole purpose is basically to show direction and to make this expression, which is the magnitude of the vector, into a vector. Its magnitude is 1, this is magnitude is 1, so multiplying it by anything doesn't change the magnitude, but this does indicate direction. So how do we read this? Well, K, like I said, we'll unpack in a second, is a constant. With any sort of mathematical expression, the standard procedure is to run some experiments, collect some data, and then try to fit the data to a mathematical expression. Usually part of that is determining some sort of proportionality constant. This is what K is. We'll talk about it, like I said, in just a second. For now, just hang on to that it's a constant, and it is a reasonably large constant. It's on the order of 10 to the 11th. 10 to the 9th. It's on the order of 10 to the 9th. Q1 and Q2 are charges. Q is going to be the generally accepted symbol for arbitrary charges, just like M is the accepted symbol for mass. Q is going to be the accepted symbol for charges. We've already seen a specialized charge, which is E. That is a very special, specific charge, but Q is our general way to represent charges. So these are two charges which are in proximity to each other that are exerting forces on each other. So you can read this as the force of Q1 onto Q2. You might be able to convince yourself with Newton's third law that the magnitude of that has to be equal to the force of Q2 on Q1. But at any rate, Q1 and Q2 are the two charges involved in this force. R1, 2 is the distance. You will be tempted to read R as a radius. It is not always a radius in this course. We will use it as a placeholder for a distance. Is the distance between the centers of Q1 and Q2. I have to write the centers because if you think back to Physics 1, you proceeded by, at the beginning of class, considering everything to be what's called a point mass. That is, it's a mass that's concentrated at a true point in space with no spatial dimension, and then you developed terminology to talk about that, Newton's second law and so forth. And then you started considering extended masses, objects that were rotating and that had moments of inertia and things like that. And at some point you saw the Newton's universal law of gravitation, which in form looks very similar to this expression. We'll make the comparison more explicit in a second. But the caveat with Newton's law of gravitation is that The denominator in that expression was the distance between the centers of mass of the two massive objects. In this case, we're going to consider lots of things to be point charges, which are just like point masses, no spatial dimension. But of course, we live in a physical, real universe, and so at some point we've got to deal with the fact that some of these objects have an extended nature and that the charge is spread out over some sort of volume. So we're going to need to make the distinction that R12 is the distance between the centers of the charges Q1 and Q2. Notice it is squared, just like the universal law of gravitation was squared. This is an inverse square force, that is to say, as the distance gets farther away, but the distance between the charges gets farther away, the force falls off exponentially. As the distance between the charges increases, the force increases exponentially, I should say quadratically because it's squared. But this is the form of the Coulomb law, the Coulomb force law. R hat is a unit vector, like I say, a vector with magnitude 1. That's what the hat tells you. Unit vector lying along a line connecting the centers of Q1 and with the Sharpie, my Q's look like G's, and Q2. That is to say, if you draw a line between their centers, the R hat vector points along that line. Now, remember, this force can be attractive or repulsive. And so the direction of R hat will be given by examining the two charges. I'll show you what I mean. Right now, if I have this charge and this charge, we'll say this is Q1 and this is Q2. Let's say that Q1 is less than 0, that is, it's negative, and Q2 is greater than 0, that is, it's positive. Now, if these charges are opposite, we know that there is an attractive force, and so Q2 will feel a force directed towards Q1, like this. Q1 will feel a force directed towards Q2, like this. This is along the R hat direction. Notice which direction that is depends upon the actual force, or depends upon, I should say, the charge that you're examining. So there is a sign convention here. Notice, for this to be the case, if you have an attractive force, one of these charges has to be negative. If one of these charges is negative, what you get is a negative out of this expression. Very often you will see Q1 and Q2 written in as a modulus with the absolute value symbols. That is totally fine. What they're doing is they're determining the magnitude and finding the direction by inspection, which is basically what this amounts to. If one of these is negative, I get a negative sign here. I'm going to interpret that as an attractive force. If both Q1 and Q2 are negative, I get a positive sign here. If both Q1 and Q2 are positive, I get a positive sign out of this multiplication. I'm going to interpret that as a repulsive force. If that were the case, I will draw it over here. If this is Q1 greater than 0, Q2 greater than 0, Q1 feels a repulsive force from Q2, which is directed like that. Q2 feels a repulsive force from Q1, which is directed like that. So if you're looking for the actual force, you need to look at a specific charge and determine the force on that charge, because the direction is opposite in both cases. Now, how that works out in your particular coordinate system just depends. This R hat, in some cases, functions as a placeholder. Like I said, you'll be tempted to read it as a radius. The confusion comes in there because we will do problems in what's called a spherical coordinate system where the radius is an actual direction, and it's really tempting to read that R as the radial direction, and we will. But we'll do some problems in Cartesian coordinate systems where we have x hats and y hats and j hats. In that case, the r would just get replaced by an x hat, y hat, and j hat. So in some sense, you should think of this as a placeholder for some directional vector, which will be obvious based on whichever coordinate system you are using. So this, in a nutshell, is the Coulomb or electrical force. Now, I want to make some comparisons with the Newton's universal law of gravitation. I find, and will continue to proceed in this course, with using gravity as an analogy for lots of things electrical. I like gravity because we all experience it on a daily basis. We're all pretty familiar with it. And you've seen this expression before. So let me just remind you of Newton's universal law of gravitation. Sorry. R12 squared. And then there may or may not have been an R hat attached to this, depending on who your professor was and what class you're in. We'll just leave it here as a magnitude. This is the gravitational force. Let me get rid of that. And let me just remind you of the Coulomb force we just wrote down. I hope you see some similarities. They both involve two quantities. In the case of gravity, there are two masses. In the case of electricity or the Coulomb force, there are two charges. They both involve a distance between those two quantities, which is squared, and they both involve a constant. Newton's universal gravitational constant is on the order of 10 to the negative 11th. It's a really small number. Gravity is actually a pretty weak force. You can overcome it just by jumping up into the air. Now, gravity wins in the end because you don't have anything on which to apply a force to fight gravity once you're in the air. But you're able to overcome gravity pretty easily just by standing up or jumping into the air. The electrical force, as I said, this by magnitude, this number is about 8.99 times 10 to the 9th. There's some units associated with that, of course. You probably figured it out. It's Newton meter squared over Coulomb squared to make the units happen here. To leave you with newtons, this should be a meter. Sorry, Sharpies. Don't worry about the units for now, though. 8.99 times 10 to the 9th. Remember, gravity was on the order of, I can't remember the exact number, but it's on the order of 10 to the negative 11th. That means that the electrical force is 20 orders of magnitude greater than the gravitational force. Of the four fundamental forces in the universe, these are two of them. Gravity is by far the weakest, and Coulomb is the next strongest. It's a much more powerful force than gravity. We don't normally notice it being such because when we deal with gravity, we typically deal with really large masses like the mass of the Earth or the mass of the Sun or the mass of a black hole. The mass of, remember, an electron, not the mass, the charge of an electron is on the order of 10 to the negative 19th coulombs. And so we usually deal with pretty small charges. So the electrical forces we deal with on a day-to-day basis are usually pretty small. But don't let that fool you. The electrical force is quite significant. All right, so I should point out that this constant K is called the Coulomb constant. It in itself is shorthand for a collection of other constants. This is actually defined from this 1 over 4 pi. And this constant, epsilon naught. 1, I'm assuming you know. 4 and pi, I'm assuming you know. Epsilon naught is called the vacuum permittivity, or the electrical permittivity, however you want to say it. It's just another constant, and it becomes tiresome. Again, we're physicists, we're inherently lazy. It becomes tiresome to write 1 over 4 pi epsilon naught. So we wrap all that up because all of these are constants in this Coulomb constant K. When I was an undergraduate, we used K in my freshman physics course, and then in my sophomore E&M course, my teacher's like, well, we don't use K, that's weak. We use 1 over 4 pi epsilon naught. And so we were all like, well, we're good physicists now. We use 1 over 4 pi epsilon naught. And then I got to grad school and everyone was like, why are you writing that? Just write K. It's a lot easier. And it is a lot easier. So I do want to point this out, though, because there will be certain situations where we use this expression, certain situations where I just take the shortcut and write K. Either one works for me. It's not a big deal. This is a constant. All of these are constants. And we'll talk more about the vacuum permittivity, what that means, and how that relates to the universe around us as we get farther along. So this is the Coulomb force law in a nutshell. Once you have it, it is easy to find vector sums of forces if you have multiple charges acting, if you have more than 2, right? You just do this force law for every pair of charges there and sum up the vectors, and we will be doing some examples of that as we go on. All right, that concludes this section.